Today we'll be beginning chapter 2.3, which is transfer of thermal energy. Let me just put down the heading over there. And we will be studying about the three different physical processes, mechanisms by which thermal energy is transferred between objects or environments. Those are conduction, convection, and radiation. Of course, this radiation that we're talking about does not have anything to do with nuclear radiation. It is about the transfer of thermal energy. So let's start off with conduction. So what is conduction? It is the flow of thermal energy through matter. Right, from places of higher temperature to places of lower temperature. And what's important over here that this happens without movement of the matter as a whole. Without movement. Right? So it is the flow of energy through matter from higher temperatures to lower temperatures within the matter. And so what's happening, it is, right, if you have an object over here, right, we're not specifying the material or what kind, you just have an object over here, and right, you are providing heat, you are heating one end, and so the particles over here, they are gaining energy, and with that energy, right, so when you're heating it, right, the energy of the particles increases, and they're not moving in the sense that they're moving from one spot to the other, they're in their fixed positions, but along with the increase in energy, right, their temperature obviously increases, and their vibrations also increase, because we know that particles are always vibrating. And because it's happening from a region of higher temperature to lower temperature, before you heated this object, it was all at the same temperature, possibly room temperature, environmental temperature, whatever it was, but now you're providing heat. And so these guys, right, and so, right, your heat, these guys are, the temperature is rising, and with that they are then transferring that thermal energy, because the temperature, right, is the internal, right, average internal kinetic energy, right, and right, the internal energy is also the thermal energy. So they're gaining energy and they are transferring that energy to the next particles, and then that continues until, right, the heat has been transferred all the way to the end. And if you stop heating it, it will all be at a raised temperature. If you continue to heat it, then the heat transfer will continue, and so with time the other end of this object will continue to get hotter and hotter and hotter. The part which is experiencing the heat directly will obviously get hotter first, and then the heat will be transferred via the raised energy and thermal, right, raised energy of the particles and their vibrations, right, it will be moving along the object. Now, right, does this happen equally well with all objects? No, right? You can talk about conductivity in terms of heat, right? So there are good conductors of heat versus bad conductors, or poor, not you can say poor conductors. They don't do it very well. So examples of good conductors of heat are definitely metals. And you may have experienced this if, for example, you have cooked food and you are using a metal spoon or any metal, spatula or something made of metal to, while cooking in the pot that's on the stove. And so with time, right, that spoon that's in the pot, right, this part's in the pot. This is supposed to be a pot with food in it, and obviously the heat's right here. And so, right, the part that is in contact with the food in the pot is going to get hot first, but over time you will feel that the edge of the handle has also gotten a temperature rise, and that's because the thermal energy has transferred throughout that metal spoon. Have you ever experienced this?
Yeah.
Right? And so that's basically conduction in action. Right? You may have experienced this if you are using a metal spoon to, or any metal object in any hot, you know, body or mass of something. For example, eating hot soup with a metal spoon, right? The weather is getting chilly, and so soups are in season, and so the spoon would get hot if you're right if it's metallic. Poor conductors of heat are, for example, wood. And the reason being that the particles do not as efficiently transfer the energy. Right, so these guys are efficient in the transfer of thermal energy. Right, and these guys are non-efficient or not efficient. And so, right, the transfer happens, but it's very slow. So that is why, right, you normally have wooden utensils, well, not utensils, but wooden spoons and spatulas to use in the kitchen for cooking purposes. And that's because even if the the broader end of the spoon in contact with the food or the pot is getting hot, the handle won't be as hot. It will still be relatively cooler, and still you'll be able to handle it with your bare hands perhaps. Why? Because the heat is not transferred efficiently, right? So that's not happening. And so, right, wooden utensils or even plastic, right, although plastic does get hot over time, so it does eventually happen, right? So wood's a very good example. Plastics also are not very good conductors, but they do, right? I mean, again, saying not good conductors means that it is happening, but not very well. So that is the concept of conduction. They've given an experiment, right? Even among metals, right? The heat conduction of metals varies. So even the good conductors are not all the same. So they give an experiment in the book where they have four metals: copper, iron, aluminum, and brass, and they heat all of them. And what they see is that copper is the best, followed by aluminum, brass, and then iron. Right. So according to what's the experiment, aluminum is the best conductor. Sorry, copper. Copper is the best conductor among the four that are being compared, followed by aluminium, and then you have brass, and finally iron. Now, right, how fast is the thermal energy conducted? It depends on the cross-sectional area and the length and the temperature difference. All right, so these are three factors: cross-sectional area. Right, so the higher the more the cross-sectional area, right, the faster it is. Faster is the conduction. Right, how short it is or long it is. So distance basically. The shorter it is, the faster it is. And how big is the temperature difference? The greater the temperature difference, the more conduction will take place. Now, the poor conductors of heat are also sometimes called insulators because that's what they're used for. So in this case, depending on what's happening, they either, right, do not take in or lose heat. In either case, right, they do not transfer heat very well. So another experiment that they've given in the book is they have, right, a piece of brass and then a piece of wood, and they've covered that with paper. Right, part of it is covered with paper, and what they're doing is that they're heating the part that is covered with paper. So when they, right, so this is brass and this is wood, and the green guy is paper, and the yellow is, well, basically a fire. And so when they put the flame and right under the paper that is covering the brass, the paper does not burn. And the reason they give for that is brass is a good conductor of heat, and so, right, as soon as the flame is under the paper, that energy is quickly transferred along the piece of brass, and so it's taken away from the paper. Via conduction. And so the paper doesn't burn. But when they put it under the wood, right, it burns. And the reason because is wood is not transferring that heat efficiently. And because of that, the paper gets hot and then it starts burning. So this is an example again for conduction. Any questions?
No.
Okay. Another thing that's related to conduction is that when you touch a metal object, it feels colder. And that is because the metal object quickly carries the thermal energy away from your hand. Whereas if you carry an object that's an insulator, it feels like it's at your body temperature because it's not carrying your, the heat from your hand away. So tying this in with the kinetic particle model. So conduction and the kinetic particle model. So in case of metals, what's happening is metals have beat right in the metallic structure, something that right is discussed in chemistry when you study bonding. So in a metallic structure, right, in terms of its bonding, there are delocalized electrons. So the question over here is, right, when we talk about the heat being transferred by the particles from one to the other, is it simply because you know, these particles that are experiencing the heat directly are vibrating very fast, and because of their vibrations, the heat is being transferred? Not quite. Okay, so in case of metals, they have delocalized electrons that are, sort of flowing through the entire metal, structure. And there's not just one, like there are a number of delocalized electrons that are going through the entire structure. So what happens is when you heat one part of the metal, one end of the metal, the electrons start moving faster because they're particles as well. So these delocalized electrons move, right, they gain energy and they move faster and further.
What's meant by delocalized electrons?
Okay, for that we'll have to touch a bit on chemistry, right? So for example, let's take sodium, the simplest example, right? Sodium, now I'm talking about this theoretically because, right, sodium is stored under oil and you don't use it for heating and stuff. Or let's take aluminum, that's easier. So aluminium, right, has three valence electrons or three outermost electrons, right? So electrons, atoms have shells in which electrons are arranged, and then the electrons in the outermost shell are called valence electrons or outer shell electrons, outermost electrons. And so aluminium has three valence electrons, and that's why, right, in fact, I won't go into chemistry. Let's just keep it, right? It has three valence electrons, meaning it has three electrons in its outermost shell. So what happens in the structure of aluminium, that these three electrons, right, aluminium has not bonded, it hasn't made a compound. And so these three electrons from each atom of aluminium, they become delocalized, meaning that they're moving about between all the aluminium atoms. Do you understand? And this is, right? So 3 from each, and so you can imagine how many electrons there are, right?
Yeah.
3 from each. So because they're not sticking around in their orbits, they are moving about everywhere. That's why they're called delocalized.
Okay.
Localized meaning in one place,
Hmm.
right? Delocalized meaning not in one place.
Yeah.
So localized in one place, delocalized not in one place. So the electrons move faster, they move further, and with that, right, they interact with the particles that are on the cooler region, and so they transfer their thermal energy to the cooler parts. Now, see, we're using the term cooler, which is comparative, right? So if the end of this metal, which is, being heated is, for example, at 70 degrees centigrade, then the other end, which is at 50 degrees centigrade, might be hot, but it is cooler than 70 degrees centigrade, right? So we're using the comparative term of it. And so with that transfer of energy, the cold part also becomes hot, right? After gaining the energy, the particles start vibrating more vigorously. Those electrons also gain energy, etc., etc., right? Now, this is not happening with non-metals, right? So transfer energy, the temperature increases. With non-metals, right, there are no delocalized electrons. So wood does not, for example, have any delocalized electrons. And right, or free electrons. And so they obviously cannot pass that energy as efficiently. And so, right, they don't get as hot, they don't transfer that heat. And so they're poor conductors, right? And on that same note, they are good insulators. As I mentioned, insulation is, right, trapping the heat or not allowing it to be transferred, which is exactly what they're doing. They're not transferring the heat. So it's getting chillier and you're wearing a sweater. So the material the sweater is made of, or your hoodie, your jacket, or whatever it is an insulating material. It's right. So what it does is it's trapping your body heat in the air, right? So when you wear it, there's air between your body and the sweater, and it's getting warm because, right, your body is giving out heat. But what the sweater is doing is it's not allowing that heat to escape the air to the environment, and that's how it keeps you warm. So it's trapping your body heat close to your body. So air is, you know, an insulator, right? The wool is an insulator. Other materials are also insulators. So that's right, basically working on conduction. Then there are some solids that have few free electrons. So they are not as good as good thermal conductors, but they are better than poor conductors, and so those are called semiconductors. Right, so these guys have few free electrons. They are better than poor conductors. but not as good as good conductors. Any questions?
No.
Okay. So next up is convection. And convection is how thermal energy is transferred through fluids.
Fluids are usually liquids, no?
In terms of physics, no.
Then,
Just a minute.
okay.
Fluids in terms of physics are liquids and gases, because the term fluids is used for anything, right, matter that flows, right, that moves, that's able to, so liquids can flow, gases can also flow, such as, right, the air blowing, right, that's a flow. And so air is in physics, air is considered a fluid. Okay.
Oh, yeah.
Right. uh, so, right, this, right, it is the flow of thermal energy through a fluid. Again, from, right, a region of higher temperature to, right, a region of lower temperature. But the difference between conduction and convection is here the particles of the matter are moving, right? So by movement of the fluid, right, let me add particles in brackets, itself, right? So the matter, the fluid, the water or the air or whatever other fluid you're talking about, itself is in motion with the thermal energy it has, right? It's not just, delocalized electrons, and the water does not have delocalized electrons, air does not have delocalized electrons. So how is it transferring the heat energy itself? The particles are themselves moving from one place to another. Okay. So, right, how can we study this? For example, they've given the example of adding, uh, you know a few crystals of potassium permanganate. So, in fact, I'll just put the book on screen for that one instead of typing it, writing it out on the whiteboard. Right, can you see that?
Yeah.
So, right? This is a beaker. This purple thing over here, right? They put in its potassium permanganate, and so, right, this is actually you can get it from store easily. You can try this at home. It's cheap, and so they put a few crystals, and when you put it in, it might leave a trail, a purple trail, while it's moving to the bottom. But other than that, it won't spread quickly. It will spread, but it won't spread quickly. So what they're doing over here is they put a small flame under the crystal, exactly where the crystal is, and so the water is getting heated. This guy is, the potassium permanganate is dissolving sort of in water. It is, right, by diffusion of the potassium permanganate. But what's happening is that the water is gaining heat, and so the water is warming, and then the warm water is rising up. So the water itself, the warm water that's gained heat itself is rising up. The cool water is coming down. And what that does, it sets up a convection current in the water. Right? The reason that happens is because, right, when heated, it expands and it becomes less dense. So the water, if it's even like a bit warmer at the bottom than it is at the top, right, it is less dense comparatively, right, because it is expanded, and we've talked about expansion in the kinetic particle model, and so it's going to rise to the top. The cold water is going to come down, and that's going to send up a current, and so that is how the heat energy is being transferred through the water. And with the movement of water itself, the potassium permanganate is spreading throughout the water, as you can see in the image. Right? This is a lava lamp, and if I don't know if you ever seen one in person, but the liquid inside is oil, right? And then they've got this other material, and we can see the wire going in. So there's an electrical heat source down here. So what happens is, right, when this blob comes down, right, it is heated, it expands, it becomes less dense, moves up. When it goes up, after some time, right, it cools down, comes back down, and the ones that over here, so these blobs continuously keep moving up and down through the lava lamp. Right, so that's basically convection happening. Does that make sense?
Yeah.
Okay. The same thing is happening in air. So this is an experiment, right? They have some smoke over here, and the smoke, right, they've put a candle, they've got two tubes, and they put a candle under one of them. So this part, the air is being heated, and so it is expanding, it is becoming less dense, and it's going to rise up. So the reason why the smoke over here is moving down is because a current has been set up. Air is rising because it's warmer, and so over here the gas itself is denser than air, and because the air over here is rising, it's pulling sort of the air that is cooler. The cooler air is going to come down, and then it's going to get warmed up and leave from here, and so, right, that's sort of a current that's set up. And that's the same reason why, although this is a going further topic, you get land breeze and sea breeze, right? Because during the day, as we talked about specific heat capacity, so the specific heat capacity of soil is lower than water, and so the land heats up more quickly during the day than water, and right, the air blows towards the land, whereas during the night the sea is warmer because it's been heating up all day, and right, the land has become cool because it has lost heat quickly, and so, right, the wind blows from the land towards the sea. So they've given an explanation over here as to why that's happening according to convection. It's a going further topic, but it's something that you can read the explanation to why that's happening. Right, the hot air above the land rises and is replaced by the colder air from the sea. So that's the sea breeze during the day. Right, the air over here has risen, the cooler air is replacing it. And similarly at night, right, it's the opposite. The air above the sea is warmer it has risen, and so the cooler air is coming in. So just to further explain how convection works, is that clear?
Yeah.
Okay, pretty simple. Now, next up, radiation. So I'll go to the whiteboard for that. Yeah. Right, can you see my whiteboard?
Yes.
Huh?
Yes.
Okay. So, radiation. Radiation is, just a sec, sorry. Right, so radiation is the third way in which thermal energy is transferred. And right, in this, particles of the matter are not involved. So how it happens is through electromagnetic waves that are being transmitted with the speed of light. Does not involve particles. Right, the heat energy is transferred, and in the form of electromagnetic waves. So this is something we will get into in the next unit, which is waves. So we'll talk about electromagnetic waves and sound waves and all of that. Right? It's occurring at the speed of light. Well, actually not the speed of light, right? Electromagnetic waves. These guys, right, have the speed of light. The radiation in this case is infrared radiation. Okay, and all objects emit infrared radiation, right? How much of it they emit, sorry, how much of the radiation they emit depends on how hot they are, right? Right, so it's all uh, the radiation, right, that falls on an object. Maybe, right, part of it is reflected, part of it is transmitted, so it is transferred forward, and part of it is absorbed by the object. So the object receiving this radiation, and this is, right, the part that is absorbed is the one that raises the temperature, obviously. The part that's reflected, right, it's gone back, it's not used. The parts that transmitted, it's been transferred to the next object, and so it is, right, the one that's absorbed that raises temperature. And that is one reason why in hot regions buildings are painted a light color, or the best is white, because white paint is very good at reflecting the heat, the radiation. What am I writing? White. So it reflects the infrared radiation and helps keep the buildings cooler. And that's true for your clothes as well. If you're wearing white clothes, they help to keep you cooler because they are reflecting heat that's coming your way via radiation. Now, there's just a bit left to talk about good and bad absorbers, good and bad emitters, and right cooling of an object. And then there are the consequences of thermal energy transfer, right? So how they are put to use basically, and keeping things cool or warm. The different applications of conduction, convection, and radiation. So I believe, right, I'll stop here. We'll cover the rest tomorrow, and so we'll be done with unit 2. And then next week we can start with unit 3, which is waves. Any questions?
No.
All right, so all's good. I will see you next class, inshallah.
Nice.